Hey everyone, I'm gonna be doing question two of week 6B homework. Today we're solving a problem about Young's double slit experiment. First I drew out what's exactly happening. So here we have two slits separated by a small distance, which is called D. See our two slits? And over here is the screen on the left left corner. And so that's where the light forms bright spots. And I didn't draw the bright spots, but it would look something like I don't know, something like this, like bright spots and on fringes. So from the center line to the bright fringe we care about, there's an angle theta over here. So from me. And so the light is coming through has a wavelength of, yeah. So before doing any math, we can define all the variables we're looking at. So theta is the diffraction angle. So it points to where the bright fringe shows up on the screen. So it's measured in radians or degrees. And then m is the order number, so it just counts which bright spots we are looking at from the center, like m is equal to 1, 2, or 3 since it's a count. So it doesn't have any units because it's a count. Lambda is the wavelength of the light, and so that's the distance between the peaks of the light wave, and its SI unit is in meters. So lambda. And then D is the slit separation over here. And so that's the distance between our two slits, and its SI unit is also in meters. Now for the general formula for bright fringes, in a double slit setup, it is sine of theta is equal to m times lambda over D. And so the problem tells us that angle theta is really small. So when the angle is really small, we could use a small angle approximation, which is sine of theta is equal to approximately theta in radians. So that means we could simplify our equation to theta, yeah, I'm just gonna cross that, is equal to m times lambda over D. And so this equation tells us that the angle theta is directly proportional to wavelength lambda and inversely proportional to the slit distance d. And so now let's see what happens when we double both of the wavelength and the slit separation. So let's call our original angle theta 1. So that's our original one. So theta 1 is equal to m times lambda over d. And so now let's write our new angle, which I don't know, we'll use angle 2. Okay, so angle 2, in this new setup, we will replace lambda with 2 lambda, and we'll replace d with 2d. So that means theta 2 is equal to m times 2 lambda over 2d. And so if we look at the fraction 2 lambda over 2d, in the 2's in the numerator and the denominator, they both cancel each other out. And so that means that would just leave us with theta 2 is equal to m times lambda over d. And so that is the exact same expression as we started with say theta 1. So that means that theta 2 is equal to theta 1. So since the two cancel each other out, doubling both the wavelength and the slit separation leaves the angle completely unchanged. Therefore, the angle does not change. Thank you for watching.